Okay, let's go ahead and get this started. We got a lot to cover today. Thank you all for joining us wherever in the world you may be. My name is Matt Sanders. I'm the program director for the Pacific Ocean Energy Trust, and also your tech support for today's webinar. If you have any questions or comments, feel free to find me and email me, or however you may need to. The title of today's webinar is Subsea Transmission Solutions for Offshore Wind between California and Oregon. I don't think you have the option as attendees to have your video or your volume on, but if you do, please go ahead and mute yourselves just so we don't have any complications there. Any questions? It looks like we've already got a couple folks who know how to use the Q&A function. But please use that Q&A at the bottom of your screen to ask questions, and then Jason will be moderating the Q&A at the end of the session. If possible, we'll go ahead and answer questions during. But we do like to take questions at the end there. And then last, this is being recorded, and we will go ahead and make this recording available on the POET website in the next few days. Takes a little bit of effort to get that up there. So we appreciate your patience. And with that, happy to hand it over to Jason.
Excellent. Thank you, Matt. And thank you all for joining us today for this next installment of the POET webinar series. I want to start by thanking our sponsors, Power Engineers. Eric Hale and his excellent team have contributed to help make this webinar available today and to promote POET's mission of addressing climate change through the responsible development of marine renewable energy. So thank you, Power Engineers. We do have a lot to cover today. Matt, if you want to advance that for us. We're going to post the we've got our agenda here. We're going to look at the opportunities and need for a subsea backbone transmission solution. We're going to look at the transmission basics, and we're going to look at what a backbone transmission system would look like, what that would entail, and we're going to finish with a presentation on planned mesh networks and the regulatory policy framework to support those networks. Next slide, please, Matt. Here are your presenters today, and we're going to make the bios of these folks available on our website. When you go to the webinar, you can see the full description, but we don't want to spend the time reading through those today, but you'll have the chance when you come back to the website. So before we get started, I wanted to make a few opening comments about this webinar, and we'll let the experts flesh out the substantive details, but I did want to take this opportunity to discuss a bit why we're doing this and what the assumptions are going into it and what our intents and purposes are. As I'm sure that the vast majority of people on the webinar today share POET's awareness of the opportunity that is floating offshore wind in the area between Northern California and Southern Oregon, where the tremendous wind resource lies. And POET's goal, in order to advance its mission of promoting responsible development of marine renewable energy to address climate change, is to maximize the amount of offshore wind that gets developed and to minimize the costs to ratepayers, as well as to the ocean and its users. And we need to do this in a timely manner. So to that end, we've been thinking about how do we achieve this goal, and this issue of shared infrastructure has arisen as what we consider to be one of the most important steps that can be taken. I know we can look to Europe and to the East Coast for lessons learned, but we believe on the West Coast, given the remote nature of the resource and the lack of shoreside infrastructure to support offshore wind in that region, that the solution here is a shared infrastructure that includes some sort of backbone transmission and the various components of that. We are well aware of the complexities, the difficulties, the challenges, the costs, et cetera, of why this is would be an extraordinary lift. But now is not the time to shy away from such efforts. In fact, it's very much the time to be leaning into such opportunities and try to make the most of them. So POET wants to advance the discussion around this concept, which is really the purpose of today's webinar. We are not proposing to lead, design, build, own, a backbone transition system. It is merely to put forth a straw proposal for a backbone transmission solution for the purpose of advancing the discussion around how this concept might be achieved. So we are aware that there are various entities that are seeking to study this opportunity, and hopefully we'll see some more announcements soon about studies that will continue to parse the various aspects of what a shared infrastructure solution would look like. At the end of the presentations today, before we begin our Q&A, I am going to ask you all to take the opportunity to post to our chat function here or send directly to me at POET the issues that you think are most important regarding this topic, issues of concern, challenges, opportunities, and thank you, Matt. So we're going to ask you to do that. Please reserve that toward after the presentations so that the chat function does not get clogged up. We're watching those, and we want to see issues of concern or technical problems, that kind of thing. So please save your comments till that period at the end of the presentations. So with that, I'm going to stop and hand it over to Bill Henry to launch today's webinar. Bill?
Thanks, Jason. Let me pull up my presentation. Is that showing full screen?
It is.
Great. So thanks, Jason. So I'll reiterate the purpose of the webinar is to advance the conversation about offshore wind on the West Coast. So what we wanted to do was introduce a straw concept or a straw proposal, maybe for discussion purposes. And I think the idea of putting something down on paper or digitally to be able to have something tangible to look at and talk about is very important as just an initial first step. So what we did to help shape that concept was ask the following questions. So I have them listed here. I'll kind of walk through them. So what is the resource potential and opportunity to develop offshore wind in Southern Oregon and Northern California using available technology? And then what of this technology is at the appropriate development stage to deploy? So there meaning commercially ready or near commercially ready. And then how may this technology be deployed to connect a large portion of the available wind resource in this area? And then what are the grid benefits of doing so? Now, I think it's important to emphasize what we didn't do. We didn't do anything beyond an initial high-level look at answering these questions. This is really more in the stage of asking questions rather than providing, deep, substantive answers. And I think the whole point of this is to get rich questions that emerge from this process. And we also didn't address onshore transmission upgrades beyond this idea of a central offshore backbone cable concept. So to look at and I'll step through these areas of inquiry. So the area of potential interest. So clearly, we looked at the bullseye right in the middle of the Pacific coast on the border between Oregon and California, where the area of high potential exists. And looking at it a little bit more in detail, what we did was look for areas where the subsea or the seafloor conditions are favorable for development. So this means areas that have flat sea floor and avoid areas with steep slopes and canyons and things like that. So there's a fairly large area in the middle, which you can see north of the existing call area and then south of the Coos Bay area, you can see up to the north. And that could have a potential in the range of 4 to 6 gigawatts. This is a rough order of magnitude. This is definitely not any type of potential study, but it is intended to inform the general scale of the infrastructure that might be needed to realize this potential. So to realize this potential, we worked on or created the straw concept for how to connect this substantial quantity of wind energy. So the straw concept is a high capacity static backbone cable system in shallow water, linking multiple fixed substation platforms to which multiple wind developers could interconnect in the future. So I'll draw your eye towards the right-hand side of this figure, which is showing the fixed platform and static backbone cable. And the reason why this is important is to be able to export larger quantities cables that are fixed onto the bottom is likely to be important. And then over on the left-hand side, we're showing one way of collecting energy from the wind farms themselves. There are a couple of other ways of doing it that I think that we're going to hear about later in the presentation. So to put a little bit more detail on what this could look like, here's a conceptual sketch of a backbone cable system in shallow water. So this is water that may be less than 100 meters in depth, with multiple fixed collector stations that are collecting energy from the wind farms that also potentially connected to each other. So the cable system connecting platforms to each other is more likely than not to be alternating current. But then export systems could be AC or DC, and they could be connected at multiple locations, wherever those locations end up being. And I want to reiterate, this is only one possible conceptual layout. There could be many others. We just wanted to put something forth for discussion. So this type of a system begs several questions, and I've put a couple of them up here. One of them is, how many platforms or collector stations do you need? So there's a physical need for these stations to reduce the total number of cables that are extending from the wind farms to shore. And an additional benefit of potentially being able to optimize and maximize the use of the available onshore grid connection points to avoid a situation where each additional wind farm developer seeks to get another onshore connection point on top of the previous one, and so on. And of course, a question about whether there is sufficient benefits of a planned system compared to this, project by project approach. And we're going to hear more about that in the rest of the presentation. And then what are the benefits of the broader Western grid? So I'll mention a couple of points about that right now. So if there is a planned system, there's a greater likelihood that that upgrades could be configured as a multi-purpose initiative, which is to interconnect offshore wind, but also reinforce interregional grid connections. And there's a couple of high-level conceptual benefits that we can discuss for the regions. In this case, the Pacific Northwest, and also California and the Desert Southwest. So for California and the Desert Southwest, increasing the technology and geographical diversity of renewables, including offshore wind, and potentially also resources in the Pacific Northwest, like wind and solar, that could help to balance out dependence on certain resource types, and provide the possibility of diversity to California solar that may be experiencing clouds or wildfire smoke or something like that. And then another benefit is the potential stronger integration with Pacific Northwest hydro for flexibility and capacity. And then benefits for the Pacific Northwest are also geographical diversity. And a big one that I think is important to note there is solar potential that can provide energy into the Pacific Northwest during the winter time, when reliability challenges are the most pressing. So with that, we'll move on to the next presentation. And I'll close by saying that to realize these benefits, we may need to, I don't think it's a stretch to say we may need to move a little bit beyond where things stand right now with energy markets and interregional transmission planning procedures. And I think it is possible benefit to look at the starting a dedicated transmission planning process for offshore wind to be able to realize this benefit. So with that, we'll pass it on to the next presentation.
Thank you, Bill. And so Eric Hale, you're up next.
Bill, you need to stop presenting, please. Oh, there, I've got it. All right, you should be able to see my screen. I'm Eric Hale, and I'm going to present today on some basics of interconnections into the transmission power grid. And I want to start off with a cautionary tale. And this is the story of Mesa Energy and their attempt to invest in wind energy. In the summer of 27, their CEO, Mr. T. Boone Pickens, made a public announcement that Mesa Energy was going to make a large investment into wind in the panhandle of Texas. The following year, they placed a large order for wind turbines that were going to be delivered and installed in 2010. However, they didn't have a realistic plan to integrate it into the grid and to basically get their interconnection planned and approved. Although they did budget $2 billion, which sounds like a lot of money. However, it proved to be inadequate and their project wasn't able to proceed. However, this led to a project called CREZ, or the Competitive Renewable Economic Zone in Texas, that ERCOT moved forward with. And the budget for that was in the order of $60 billion. And it kind of depends, soft number, it depends on what you include and don't, but it gives you a feeling that you need to make sure that you're taking into account the interconnection costs in any renewable program and investment. Okay, today I'm going to cover the following topics. I'm going to give you a technical description of what a wind interconnection looks like, and I'm going to use examples from onshore, but the same basic building blocks will apply to offshore wind. I'm going to give you the building blocks. I'm going to show you a one-line representation of this so that you can combine into each of the turbines into a larger system. And then I'm going to show you how that then forms into a collection substation, discuss some options for that, and then from there show you where you would make your connection either to shore or to the backbone that Bill was referring to and that Steve will be talking about soon. And I'm going to also discuss a concept called the point of interconnection and what that means for these systems. And then I'm going to conclude with a discussion on paths forward so that we can actually take the next steps to interconnecting deep water wind. Now, in my world, there are three kinds of interconnections. You can interconnect new loads, think data centers, small new cities. I even did an interconnection for a ski resort once. Or you can interconnect new transmission lines or new generation. And those are the three types. And today we're going to be focusing exclusively on new generation. I'd like to start off with the anatomy of a wind farm. This is a pretty picture of a wind farm in a nice winter setting. And the idea is up here in the head that's at the top of the shaft, it's called the nacelle. And that's where there is actually a generator that when the blade spins the generator and it generates direct current. You have a device then that is fed with a direct current called an inverter, and that creates AC out of the DC, and it's still at low voltage. Then there's a cable that will run down the shaft of the turbine to a transformer at the base of the turbine that will transform the low voltage AC to 34.5 kV. Now, I like to communicate by sketching things on whiteboards, and so you're going to see that in the next couple of slides. And what I showed you in the previous picture, I'm depicting here. There's the generator, AC, low voltage AC, goes down to a transformer, And then you have cables that are buried in the ground, and these are energized at 34.5 kV, and they're taking the power from that wind turbine and daisy chaining it to the next one and then on to the next. And in a one-line representation of this, you have a generator here, and I'm showing for this example 5 megawatts. Current generator technology can go higher than this, but it's a nice convenient number to show you what I'm trying to convey. So it goes from the generator through an inverter, then through the inverter transformer, and then the cables are run underground. The first one is going to have 5 megawatts in. Now these cables, there are actually 3 of them that are bundled together, and combined, they're probably about as big around as your wrist. And again, on land, they'd be buried underground. In the ocean, they're going to be on the ocean floor, and if possible, buried a couple feet down into the ocean floor to protect them from being disturbed by anchors or whatever. Anyhow, you then daisy chain to the next one, and at this point, you've got 10 megawatts. And then if you then, from my last slide, got you to right here, well, then we continue on, and you can see that at this point, we're up to 30 megawatts. And then we go to our collector substation with a cable that we call a home run. Now then, the home run with this type of cable, think 5 to 10 miles maximum, but ideally shorter than that. Now then, what I was showing on the previous slide is just this one point, and it's coming into this whole thing I'm showing here, I'm depicting is the collector substation. And I've got slides here in a minute that I'm going to show you examples of these from Google Earth. And this square here is a medium voltage circuit breaker, and I'll show you that on the Google Earth images. And in this case, we've brought together 5 of these. So you run them together into some bus work in the substation, and then now you're up to 150 megawatts in this example. You would then run them through a transformer to transform it to high voltage. And the example I'm showing here would be 230 kV, which is a common transmission voltage in the West. And then from there, it will leave the substation and go to the point of interconnection. Now, I'm going to show you, my first example is actually a PV array rather than a wind array, but we use exactly the same building blocks and steps to get to a collection substation. And that collection substation is right here. This particular PV array is 250 megawatts. This is actually located about 30 miles south of Las Vegas. So as we zoom in on the collector substation, you can see here, if you look closely, that there's a transmission line that leaves and heads off to the left on the screen to the point of interconnection. And then you can see that transmission line here. And as I zoom in, you can start to see the feeder breakers, which are right here. It's these devices here. And each feeder breaker in this installation has 25 megawatts. And you can see that there are 5 on this side, 5 on that side. So what's going into this transformer bank is 250 megawatts. Now, my next example is from the Tehachapi region in California. And this is a pretty classic wind farm. And this little dot in the middle, that's the collection substation. And you can see the wind turbines. You can actually see where they've run the daisy chains. So as I zoom in, there's actually, in this instance, there are 2 collector substations that are right next to each other. I'm going to zoom in on this guy. And you can see 5 feeder breakers going through a transformer. And then in this case, you have an overhead transmission line at 230 kV, and then it goes off to the point of interconnection. This is a really common architecture, and you're going to have something very similar to this when you deploy wind offshore. It simply is how you have to collect the energy from the individual turbines. Now then, let's spend a moment and talk about that high voltage connection that in the case of the examples I showed you, we're going off to a nearby substation. However, you can't use, for obvious reasons, overhead transmission in the ocean. You have to use insulated cable. Now, overhead transmission can go hundreds of miles if you're using 500 kV. However, you have a problem because in the ocean, you have to use insulated cable. And there's a physical property of this cable called capacitance. And the capacitance is going to limit the length of the cable to roughly 50 miles. There's a few tricks you can play to get some more distance out of that. But if you're going to use AC, you're going to be limited to this. And this is one of the reasons that high voltage DC is being considered for this purpose and is a likely solution if we're going to go distances with cables on the ocean floor. Now then, I'm showing you here a picture of a high voltage DC terminal. This one happens to be in Silmar, California, and is the southern terminus of the Pacific DC intertie. And for scale, this line here is 500 feet. So you can see that this is a large installation. Now, this is a really big one. This is 3 gigawatts or thereabouts. And what we would use at sea would probably be more compact than this, but not by a lot. I'm showing this so you get a feel for the scale of an HVDC terminal and what an important, significant installation this would be. So this is my summary slide for interconnections for the portion that is at sea and is going to go to the point of interconnect, presumably the AC or DC backbone that Bill had been describing. For upwards of 100 megawatts, and if you're within 20 to 30 miles of the shore, you actually don't even need a collection substation. You could actually take this to directly to shore, and it would be the easiest way, but you're tremendously limited. And 100 megawatts is probably stretching it on the high end. To get up to roughly 300 megawatts, or maybe a little pessimistic here, maybe 400 or 500 megawatts, you can use high voltage AC and 115 kV to 230 kV. And that will take you, in the order of 50 to 100 miles. But you're going to, as you start going into a longer length, you're going to have some technical challenges due to the capacitance of the cable. Anything above that, you're going to have to use high voltage DC. Okay, I'd like to now talk about either onshore facilities or wherever your backbone is installed, where you're going to actually connect it to. Now, the challenge is you've got to build something like what I'm showing on the screen. Now, this is one of my very favorite substations. This is out in the California desert, and this literally collects the energy of the sun and transmits it hundreds of miles to energize the lives of millions of people. And that's what we're talking about. The problem is we've got to build that either at the shoreline or at sea. And we have the technology to do it. It's just not a trivial task. Now then, the point is that we've got to create a convenient point of interconnection. And this is a system map of the Western United States. And I like to jokingly say that the grid doesn't like the beach, because if you zoom in on the Oregon coast, all these black dots are substations and all the lines are transmission lines. And one thing is, some of these dots may look like they're close to shore, but they're really not. Fairview substation near Bandon is a good, strong source, a good place to interconnect. You probably get upwards of 400 or 500 megawatts there. However, excuse me, it's well inland. So you have a relatively substantial challenge just getting to it. And from this, you can see the attractiveness of putting the AC or DC backbone actually using submarine cables offshore, although it's not the only option, but it certainly, you can understand the appeal of it. We also have a very rugged coastline in Oregon, which means that we've got to be very selective about the point that we actually do, because ultimately you have to bring the cables ashore and deliver the power to market. So at some point, you're going to have to pick a location to bring it ashore, and you're going to have to build one of these. And it's a transmission line. Personally, I think transmission lines are actually look rather elegant. They look like a Cristo sculpture going across the horizon. Now, I understand not everyone agrees with me. And so hence some of the interesting challenges that we face with this. So now that I want to summarize the onshore or backbone options, I probably misnamed this slide. I should have called it the backbone options. And this is similar to my previous summary slide, except this is what you're going to be using for that backbone. For up to roughly 30 megawatts, you can use the distribution system, and that's voltages that go up to about 34.5 or 35 kV. For roughly upwards of roughly 500 megawatts and distances that can go, particularly if you're using overhead transmission, you can go upwards of 250 miles. However, you're going to get a tiny fraction of that if you're using cables. You can use high voltage, which is upwards of 230,000 volts. Anything above that, you're going to have to use high voltage AC if it's onshore. If it's offshore, you're going to have to use high voltage DC. Okay, I want to close with some talks about what are the next steps? What are the paths forward? In our current way we develop new generation, it's independent developers that are, and not utilities, that are making the investments, developing the projects, and bringing them to market. I know these people, they're my clients, and they are some really smart folks, and they are very conservative risk takers. They need to have the assurance that what they're doing is going to work and that it's going to be a sound investment. Now then, failures in this do occasionally happen, and they are ugly. This is an example of one. This is an installation of reflecting thermal solar that's south of Las Vegas. That thing in the distance is Las Vegas. And they didn't end up performing very well when they were built. You probably won't see many of them built again. And two of my clients invested in this. One of them had contributed to their bankruptcy. The other one, while they're still financially healthy, they've sworn to never own generation again, which is really unfortunate. But it was a traumatic thing. So anyway, what we need is to have something where we can start demonstrating these technologies, and because we're not going to know until we try. And the theme here I'd like to convey is to start small but think big. And we are starting small. There's a project that I am really excited about. It's called Parkway South. And what it's going to be is a test terminal for, off the Oregon coast. And it's actually meant to test wave motion generation. And there are going to be 5 feeders that are going to run 6 miles offshore to a point that they're in about a little over 200 feet of water. And they're going to be used as test terminals. We are going to learn a lot from this, and you can follow their progress at the website that I have listed on the at the bottom of this slide. Okay, I'd like to conclude now. I've gone through the technical aspects of a collector substation for renewable power. I've talked about the onshore and backbone connection and how important that is going to be, because we have to create a convenient point of interconnection for the developers to plan their systems and deliver the power to market. And we have a great path forward, and we're going to learn tremendously from the Pathway South. And that concludes my presentation. I'm going to stop sharing my screen. And Steve, I'm going to turn it over to you.
Thank you so much, Eric. Fantastic, getting excellent comments here on the side here. So next up, we have Steve Johnson.
Okay. Do you see my screen with the title page, please?
Steve, right now we see you.
Oh. Okay, I thought we'd sorted this out. Sure.
There's your lovely family again.
Yes, indeed. How about this now?
Perfect, thank you.
Great. Okay. Good morning, ladies and gentlemen. I'm new to all of this, so I'm just learning. But Jason and I had a conversation a few months ago about this, talking about offshore wind energy in the area here, South Oregon and North California. And we were talking about how it could actually be done with existing technology. And so that put the challenge out to me to start researching all of this. So what I'm going to be sharing with you is what I found out. So what I've got from a conversation today is introduction, typical designated area equipment, how we going to, and the technology development status and the main components. So this is going to be a bit of a whistle-stop tour, I'm afraid, but I'm hoping to show you that I think it's doable. I think the technology is very close to being available. All right, there's some work necessary, but let's just go through what I've found out and I'll share it with you. So this is to demonstrate, I say, the technology. You've heard about the backbone opportunities, discussed in other parts of the web, so this supports that. And as a group, we've been discussing this for the last couple of months here. Now, although I'm showing equipment, in no way should this be considered a solution, as much more work is needed before we can say, right, this is what we're going to build. And just to help it be more realistic, I've identified particular suppliers, but it's too early to say which ones are preferred. There's a lot more work necessary here. And there's multiple suppliers in the different areas. And we were targeting about a gigawatt per allocated area, as you will have seen from Bill's earlier talk. So lining up with what Eric had been talking about for the onshore, we're still going to need for a block. If you look at this, it relates to one of Bill's earlier blocks. And it fits in with what Bill was talking, with what Eric was talking about with the wind turbines. We've got to come to multiple infill gathering systems. And these gathering systems need to go to a substation. And we'll talk more about the substation. But whilst we're out here, we're in floating or subsea systems in the designated areas, then the substation needs to be fixed platform, and I'll explain that as we go forward. And then from that, as Eric was describing, we need to have our power cable that goes to the beach. And that's up to Eric and others to define the voltage and the frequency and such like. So when I was talking to Jason, we were talking about identifying technology that was commercially available for a project. And if we go to ABS, American Bureau of Shipping, they've got a document which is called Technology Qualification Planning. And this is the number here. And within there, we will see technology stages: feasibility, concept, prototype, system, operational. Now, because we're talking about wanting to move forward positively with this in order to get electricity in the late 2020s, we're really having to concentrate on technology that is either well into prototype, that's level 3 here, or already been gone through in other stages, the 4 and the 5. I doubt, well, I would be surprised if we've got the time or the money to go a technology which is in stage 1 or 2 for what we're looking at here. Might be wrong, but we'll see what happens as we move forward. So let's go through the main elements. We're targeting the big wind turbines. At the moment, the biggest ones that are within reach appear to be the 15 megawatt. There's talk of larger ones, but this is what people are supplying now. And we've got multiple suppliers, Siemens, GE, Vestas, all very, very high quality, reliable organizations. And something to note as well, for what I'm gathering, you don't pack these too closely, but you've got to be on something like a 6 to 9 blade diameters between the turbines in order for the wind to go through the turbine and to reconsolidate it before it gets the next turbine. It's not fully reconsolidated, but it's what people are accepting. So these blades are big, 240 meter diameter. So your spacing is about 1.4 kilometers to 2.2 kilometers. This is a big distance, but then you've got big turbines here. So we're not talking small scale here. We're talking big stuff for offshore. I'll leave you to read the details, but as I on the left, but as I was looking through the suppliers, one of the hull designs, what they call a semi-submersible, which is basically a hull which is shaped specifically in order to accommodate the wave motions, wave velocity, acceleration, displacement. And I've chosen Principal Power here because I'm very impressed by what they're doing and where they're going here, and they're a local company. So I've got a very high regard for what they've got to offer here. So that's Principal Power with what they call the semi-submersible, and that's going to have catenary anchors or taut leg anchors, depending on what comes through. Now another one that hearing the people are not quite so comfortable with is the TLP foundation. I want to throw this in as a way of getting some reaction. But I know from my previous employers, I know a company called SBM very well, SBM Offshore, and they have supplied multiple TLPs in the Gulf of Mexico. You'll see this row of 4 platforms here. They're well underway. They're one of the leading companies in this technology. And they in turn have got the floating hull platform for floating wind. It's a different shape, it's different mooring systems, and they are currently developing a demonstration project in the Mediterranean just south of Marseille. So this technology is coming along as well. So there's lots of different things out here. There's steel hulls, there's concrete hulls, there's a lot there. So all this lot needs to be understood and evaluated. Now, Bill mentioned a little bit about the gathering cables offshore as we go from wind turbine to wind turbine. Here on the right, I've got 3 different schemes. The first one that Bill showed, and this is proving very, very popular with the development prototype systems that are being tested. For what they're using it for, it's providing a great solution. But I've highlighted here 2 other alternatives. One is where we run the cables down to the seabed rather than mid-water, and then run that onto a floating substation. Or we can just leave it all on the seabed and go for effectively our transformer, our substation down on the seabed. I'll come to that in a moment. But one of the problems we've got with the floating substation, you don't know if you can see my pointer, but there's an export cable here. This is a bottleneck. And at the moment, from what I can see, the largest power cable that's been installed in, and this is what we call dynamic mode, because as the vessel moves, the cable moves, it's all dynamic. The largest one that I've found is NKT's unit, that's 85 megawatts. So that becomes a bottleneck, and we can only restrict these now to what the export cable here can handle, 85 megawatts. As we go subsea though, once again, 85 megawatts. As we go down on the seabed, and I'll show you on the next slide, we can see seabed designs from companies such as Siemens and ABB, where they're able to go to higher targets for what's in, which reduces the amount of offshore equipment. So just very quickly, for those that don't believe me, this shows a Siemens subsea power grid solution. There's far more, Siemens know far more about this than I do. Very, very highly respected company. But this allows us to put everything on the seabed to bring the cables together. Now, talking about high voltage cables to beach that Eric was talking about. As he mentioned, we can go for high voltage AC or high voltage DC, depending on how we wanted to take it to the shore. But I mentioned before, there's a restriction with the dynamic cable, with the 85 megawatts, sorry. So this export cable, because it's taking the high power, it's got to be static. You can't have it moving because the technology is not there. No dynamic sections. And also the end terminations, electrical terminations, have got to be dry, above water. And that in turn results in a solution I'll show you in a moment. But there's several suppliers out there, all very well respected here, who can design and supply this cable. We're talking Nexans, NKT, Prysmian, and JDR cables. All very, very respected companies with this. And the photograph I've shown you here shows Global Marine's Normand Clipper in the cable lay mode. And you can see the ship here, and you can see there's a reel in the middle from which we can reel out the power cables through the tensioning system and down onto the seabed here. So it's all, the equipment's there, and there's other larger boats on the market as well that can handle the larger cables. So once again, all very doable. As we move forward to the, Eric mentioned the need for substations. Well, this is a typical offshore substation. This is from the North Sea. And you'll see, I don't know what power this has got, but I've seen some of these that are being built now for a gigawatt of power. Once again, above water, you'll see it's on a steel support structure now rather than a floating structure. But this ensures that the high voltage cables are in the static mode because they're running pipes down from the top sides to the seabed. We've got dry connections. Now for 1 gigawatt, what I'm seeing from a North Sea project is it's about 3,000 tons. Half of that's electrical equipment and half of that is structural steel. We've also got work with this backbone system in order to find the optimal location and water depth, 2 key items here, where this would go. We can't go too deep because the water depth is too deep for the support structure. We can't put it on the beach because that's not going to be very acceptable. So we've got to work out where these have got to go. And that's an amount of work here to do. The latest ones in the North Sea are now unmanned. So all of this operates without any manned intervention. You'll see a helideck top left of the yellow structure. So you can get access to it readily, easily. Support structure, here at the moment, it's showing steel, but we could also go for a concrete support structure. Both designs are well known and well respected in the offshore market. And supporting it, you'll see a floating crane, and that was from Subsea 7. So thank you, Subsea 7. We're going forward. Once again, there's been debate within the team, and really we want, as Jason mentioned, we need your support here as well. But we will be looking at typically to develop a first pass schedule, identify key decision points, and incorporating the BOEM guidelines on schedules and work needs to be done at different stages. Consider, as Jason mentioned, an interdisciplinary advisory team to guide this opportunity further. If we can get some monies, then contract an engineering contractor to define a typical offshore layout, develop high-level cost and schedules as input to a project-wide economic analysis. And then, as Eric was mentioning, we need to understand better the onshore reception location facilities and then build out all of this as an integrated solution. As we move forward, we need to document the design basis. And these are all the things that's going to be affecting the design. And we go through there, you can see the list. And I saw one of the questions to do with bird life. Well, that needs to be defined as to how we work that issue as well as we go forward. But you'll see some of the main ones, and there'll be lots of others as well that needs to go in. And this will be taken forward. We've also got to identify and incorporate code, standards, regulations. And if we see any gaps, these needs to be highlighted. But this again is a major exercise. On the technology side, although I've shown you technology that's currently available, we've got to really understand who the key suppliers are, what are the current capabilities and future plans, really understand what the technology qualifications are, and are there any gaps that need to be closed. But not only have we got a selection of equipment, we've now got to work out how best to put all this together as an integrated solution. When you buy a car, you don't buy a carburetor, you don't buy an engine, you don't buy some wheels, you buy a completely integrated solution from companies such as Ford, which have put it all together. So that's the equivalent of what needs to be done here. And then a gap closure plan with schedule and cost estimate for preferred suppliers. So there's a considerable amount of work here as we go forward to make this practical. And I just wanted to give a thank you as we go through here. I've had photographs from Siemens, Principal Power, SBM, Siemens again, Seaway 7, Global Marine, to help with this presentation. And it's been fantastic talking to the others in the POET group and other SUT individuals that supported this initiative. It's really been a great eye-opener for me to help understand this. And if you need to know more about it, either contact Jason or myself, and we can talk further. So thank you very much, everyone. It's been a pleasure providing Jason and his team support. So I'll now stop sharing and pass it on.
Thank you so much, Stephen. Excellent. And for our final presenter today, we have John Wellinghoff. I understand John doesn't have a presentation, but looks like his video is up. We'll let you get started.
Thank you, Jason. Yeah, I've got my video up, but I do not have slides. I'm going to talk about a pretty dry and boring subject to a lot of people, and that's regulation and cost recovery, which are two keys here to getting anything done with respect to any electric infrastructure project in the U.S. And this is really certainly a notable one that we all, I think, want to move forward as fast as possible. It appears from the, the overall tenor of this webinar and from the panelists that there is some level of consensus and I think support around the idea of a backbone transmission line along the West Coast to be a gathering point for multiple wind projects. That conclusion hasn't been finally reached on the East Coast, where they're developing wind projects. Multiple states there, including Virginia, Massachusetts, New York, Maryland, are all allowing their utilities to, through PPAs, purchase power agreements, contract for offshore wind. There is some level of concern that in doing that, each one of those projects will be using what they call radial generator lead lines. That would be a interconnection line from the individual development on to shore for each one of these projects. So you'll have multiple lines going to shore all along the East Coast from each one of these projects, which will be an environmental disaster, will be an economic disaster, in my opinion. And that opinion has been supported by a number of studies by the Brattle Group. Brattle's done a study on Massachusetts and a study on New York area, and they've concluded in those studies that the installation and utilization of a backbone system is much more economically advantageous by billions of dollars, reduces environmental impacts, and has other benefits, multiple benefits for both consumers and the environment overall. So, you know, if we do agree that a backbone system is one that will be the most robust, efficient, and expeditious to provide for effective development of those valuable high capacity resources that the West Coast has offshore, then you know, we need to figure out how to proceed to do that. Well, number one, we need to understand that the jurisdiction for high voltage transmission in this country is under the Federal Energy Regulatory Commission. I was the chairman of the commission for 5 years. I was a commissioner for 7 of those, for 7 years, 5 of which chair. And during that period of my tenure, I was responsible for, with my fellow commissioners, putting in place an order called Order 1000. Order 1000 is the order for transmission planning and cost recovery. So all transmission planning in this country, with the exception of Texas. Texas is not under FERC's jurisdiction. It is the only area of the U.S. that is actually not strongly interconnected into the U.S. and therefore not considered to be part of the interstate transmission system, so therefore not under the jurisdiction. But all other parts of the country, there is a requirement under Order 1000 that there be regional transmission planning conducted. So each region has to ultimately designate entities to do the planning and tell FERC who the planning authority is. In areas where there are independent system operators and regional transmission organizations, which there are 6 areas under FERC's jurisdiction, those entities are the regional transmission planner under Order 1000. In California, for example, they have an RTO, a regional transmission organization. It's called the California ISO, the California Independent System Operator. They do the Order 1000 planning for all transmission in California under their footprint, and do that planning under the auspices of the requirements in Order 1000. Outside of California, along the coast to the north, Washington and Oregon, there is another planning authority. It is called Northern Grid. It launched in January of 2020. It subsumed the planning authority of 2 other sub-regional entities that were there, called Columbia Grid and Northern Tier Transmission Group. So it it does the planning. It's composed of the utilities in the region. In fact, it's composed of the utilities not only of Oregon and Washington, but also of Wyoming, Utah, Montana, and Idaho, and little parts of California that are not in CAISO per se. So that's a different planning authority under those utilities who do this Order 1000 planning on typically a yearly basis, that plan for new transmission. And part of that new transmission would be this backbone. Now, if this backbone were to extend beyond California, out of the CAISO planning authority, then there would have to be interregional planning between both CAISO and this new Northern Grid entity. They would have to coordinate in some way. It gets a bit cumbersome to do that interregional planning, but I think there's no question that a backbone grid, potentially offshore for offshore wind, should extend beyond California and extend up into the Oregon shore. There was some discussion, I think it was Eric talking about, where you would interconnect on the coast. And Eric also did talk about, obviously, that it should be an HVDC line, that an HVAC line has capacitance limitations, and you can't go much over 100 miles. So if we're going, hundreds of miles, to get gigawatts of offshore wind developed, which I would contend that we really need to develop facilities and connections to onshore connections that look out, 20, 30, 40 years in the future. We got to optimize the maximum amount of wind development that we can do offshore. And so we have to have those onshore interconnections, ones that can be as robust as possible. I can think of only 2 areas onshore currently at the coast, along the entire coast from Washington to Baja to the tip of California, that are robust, and that's the 2 nuke plants, San Onofre and Diablo Canyon. They're both going to be decommissioned, but they may be potential interconnection points because of the level of delivery and that you could make at those 2 points. But this is all part of the planning that needs to be done. So number one, someone needs to be in charge of the planning. And is it CAISO? Is it CAISO in combination with Northern Grid? Or is it some other third entity that FERC would set up? And FERC has authority to set up an offshore wind planning task force that could be composed of representatives from CAISO and Northern Grid. I recommend that be done on the East Coast. In some testimony that I presented to FERC a while back, I believe that that testimony has been distributed out here and is available to all the participants. It would be an interregional task force specifically for the purpose of looking at the planning for this offshore backbone system on the East Coast, and you could do a similar thing on the West Coast. But someone needs to be the primary entity responsible to do that. And then there is the little issue of who pays and how you get it all paid for. Under FERC rules, under the cost allocation and cost recovery provisions of Order 1000, the basic principle that you operate under is beneficiary pays. Whoever benefits from the new transmission system, and let me back up a minute. When you do planning under Order 1000, you can do it under 3 different criteria. One is you can do it for reliability. You can plan a new line because it needs to be done to maintain or improve the reliability of the system in the area where the planning's done. You can do it secondly for economic reasons, i.e. you're lowering congestion, you're increasing throughput, so you're going to reduce costs for consumers, and ultimately you're going to put in a new line to provide that. Or you can do it for a third reason, which is public policy, which I think falls in primarily to what we're doing here, and that is, delivering renewables to meet the goals of states that have renewable portfolio standards or low carbon reduction goals. It could be a public policy goal for a state, even though it's under FERC's Order 1000 federal planning authority. And that's specifically called out in Order 1000, or it could be a public policy goal for the federal government, a larger public policy goal. And to the extent that under the Biden administration, there may be passed specific executive orders and or legislation that accomplishes what the Biden administration has announced as their goal to decarbonize the grid by 2035. That could be another public policy goal and a rationale for ultimately planning and providing for cost allocation for this kind of a transmission project. So when you're doing the cost allocation with respect to the beneficiary pays principle, how do you determine who the beneficiaries are? This offshore wind going into California, going into Oregon and Washington, does it only benefit those residents? Does it benefit the residents further throughout WEC, through the entire western grid all the way to Colorado, ultimately, and Wyoming, Montana, and New Mexico? If it does, you could then ultimately spread the costs over the entire interconnect. And in the east, there are certain lines that are spread over entire RTO regions, like PJM, which is a very large RTO from New Jersey all the way to Chicago, and encompasses, I think, some 13 or 14 different states. There are a number of large high voltage lines that have been put in place in PJM that the costs have been spread over the entire area, as well as MISO, the Mid-Continental ISO, goes all the way from the Dakotas down to Kansas. And again, that wide area, there are lines that the costs have been spread. So we could look at spreading costs potentially as one way to do it. Another way is to do it through merchant transmission, where if you had someone who stepped up who wanted to ultimately have this transmission be on a pay-as-you-go basis that they think they could make money from, that's a potential another alternative. And there may be, in legislation through the Biden administration, federal support, loan guarantees, and other federal support for building out this kind of a transmission system. But we have to figure out who's going to plan it, who's in charge of doing that, and who's going to pay and how they're going to pay. And those are the two big issues that we've got to resolve if any of this is going to get done. So I will stop with that and see if we can go to questions, I guess. Jason, thank you.
Thank you, John. Thank you for that presentation. And indeed, two very sticky questions that we will not answer today, but we will address over the coming years. So with that, Matt, beat me to it. Thank you. So before we jump into Q&A, I want to remind you what I did at the beginning, which is that what we're doing today is a very preliminary sketch of what the future of transmission might look like to support offshore wind development concentrated in the area between Northern California and Southern Oregon, for the purpose of maximizing the amount of that generation to meet our energy goals and to meet our climate goals, but to do so in a way that minimizes cost to ratepayers and that minimizes impacts on the ocean and ocean users. So doing something as remote as possible from concentrated areas or areas with ecological features is important. And the planning process for that is really just beginning along the West Coast. Many of the questions that have been posted today are extremely relevant questions that are certainly beyond the scope of today's sort of technical discussion of transmission, but are exactly the kind of relevant issues and concerns that will need to be addressed over the coming years. So one of the ways to help inform this is to hear from you, and we're asking you today to do what I'm asking here with the next steps. Please feel free to post comments to the comments section, your thoughts on issues that need to be addressed. I've recorded everything that's been submitted already, but feel free to add additional thoughts. And in the future, if you want to chew on this for a while, please do reach out to me at the address you see there, and this will help inform our thinking on and how we can lead on this effort moving forward and make sure this is done, whether it should get done, if it can be done, and if so, how it gets done. So with that, I want to invite questions, and I have started a list here. I'll go ahead and moderate this Q&A section. We have about 30 minutes, and I'm just going to start from the beginning and ask the questions. I think this first one obviously is a John Wellinghoff question. You just heard a primer on this question, but John, you might want to, if you want to take this opportunity to flesh it out any further. But who pays for the infrastructure? The question says offshore wind developers, the states, the feds. Additionally, what is the expected cost, and is that factored into the overall cost of the electricity? John, you want to try to respond to that, to add anything additional to what you've already said?
Well, first, I'll say that what everybody has to remember is that the consumers pay for everything. So yes, ultimately, whoever's going to consume the electricity is going to pay for it. It's just a matter of how you spread it out and over what period of time you do it. Traditionally, when a new renewable project was interconnected into the grid, what would happen was the developer would ultimately pay for that interconnection to the, from their development project to the point of interconnection. They'd have to pay for that, and they'd have to pay for any network upgrades necessary to make that interconnection reliable and work for the rest of the grid. And then that developer would have to incorporate those costs into the purchase power agreement for the sales of that particular project. But I think here we have to look at this differently, because this is much larger scale, and we're looking at multiple developments of projects. There was a project in Southern California in the Tehachapi wind area where FERC approved a process where there could be a spreading of costs over all of the Southern California Edison consumers for these interconnections as each wind developer came on, and then there was reimbursements from the wind developer. So there are, mechanisms that FERC has used in the past to spread the costs initially and then get recovery from the developers, who then will incorporate the costs into their price of the sales of electricity they're making, but then ultimately the ultimate consumer will pay those costs.
Thank you, John. Moving now to the next question. One of the issues we have run across in California is deep water canyons that come very close to the shore, and issues and concerns with running transmission across those canyons. This person would like expert opinion on if the cable technology can run across canyons, perhaps what the options for this issue, and concern if there are deep water canyons in the area of discussion between Humboldt and Coos Bay. I'm going to start with that. I'm going to let anybody else presenters today, because I'm not sure that any of us here today is an expert. I have, however, had some conversations about this topic, and the short answer is currently you cannot suspend a cable over an open canyon, especially in the distances that we're talking about as are identified in the Schatz Energy Lab work. I encourage folks to go to the Schatz Energy Lab. There are a number of studies there that are related to offshore wind, which point that in fact address this issue to a certain extent. The working assumption is that you would not be suspending cables. There are currents and forces there that would wreak havoc on a cable, and so the working assumption is we would have to figure out an alternative, bringing the cable closer to shore, going around the canyon and taking it back out. Would anyone else on the call today, presenters, like to weigh in on that?
Jason, what you said is correct. It's to lay cable on the seafloor, you really need area that's going to be stable. So you've got to avoid, steep slopes where you're going to have landslides. You've got to avoid areas that are seismically active. And there are some real monumental ocean features out there. The equivalent of the Grand Canyon. And yeah, it's not going to be practical to span those. You'd have to come in shore close and before the canyon started. Anyway, that's my thoughts on it.
Yeah, and if I can add to that as well, please. There's a report on this same subject out there. We read that. We discussed it between us. We looked at the seabed topography, the chance of coming to the east side of the canyons, the chance of going to the west of the canyons. We discussed it with Nexans, the power cable people, and what we got the feeling is it's not currently available for what we can see, so it didn't come within our remit of what we can build in the near future. More than likely it could be built later, but not within the timeline that we're looking at the moment. I hope that helps.
Yes, thank you. Moving on to the next question here. Another question for John. There has been little transmission development in the Northwest and almost no merchant transmission development in general. How do we get policy support and coordination going between the Western states to address transmission needs for offshore wind and other renewable energy? Will it require the Biden administration to make that happen?
Well, I think it will ultimately, and fortunately, we do have in the Biden administration, an office in the White House that's responsible for coordinating these issues and trying to move them forward under Gina McCarthy. But also, I think the other thing that we'll have to do is we'll have to do the studies to be able to demonstrate to people the benefits. I mean, that's really what it all comes down to. I mean, that's why, in fact, in the West, we've gone from just the California ISO having an independent system operator and market in California to now having what we call an energy imbalance market that is run by the California ISO for some 20 or 30 other entities in the West. So they have a sort of a market, independent market light going on throughout the West now. And that is being done because they understand the literally billions of dollars of benefits by having California run this independent energy imbalance market for them. So we're going to need to do the same thing to show what are the benefits of offshore wind, how those benefits can inure to all of the people in the West. And if we can show that through some comprehensive studies, then it's going to be a much easier sell with the state governors and state energy offices and state PUCs, that are going to try to push back on this. But we need, leadership from the Biden administration. We need leadership at FERC. I think we have it there. And then we need those entities to ensure that they have full and adequate studies that they can then go convince people at the state level to buy in.
John, I'm going to take the prerogative to ask you a question myself, and that is as you pointed out, we don't have the equivalent of a CAISO in Oregon per se. In other words, we don't have a regional transmission organization, and I'm sure you're aware, there is a movement in that direction. How would an RTO improve this situation in general for integrating large amounts of offshore wind?
Well, if you had an RTO across the entire West, in other words, a unified RTO, you would have economic dispatch being done everywhere. So that offshore wind could be better dispatched, and it would be more economical for the developers of that offshore wind to be able to sell into an RTO rather than to sell into individual balancing authorities throughout the West as we have now outside of CAISO. So there would be benefits to the developers. There would be benefits to consumers, because consumers would literally save billions of dollars by that economic dispatch across the entire footprint as well. But it would make optimum use of this wind energy if we had an RTO throughout the West.
Thank you. The question I answered on live, typed an answer, but I'll go ahead and address it now. And the question was, can you clarify the number of feet, the depth the cables are buried on the ocean floor? And the general answer to that is basically between 1 meter and 2 meters. It's done routinely throughout the offshore wind sector, wherever there's a sandy bottom where you can bury the cable. It is buried, and normally between 1 meter and 2. And they don't only violate that when you run into areas where the cable has to go over the top of exposed rocks, et cetera, in which case they are often covered with a concrete blanket, essentially, that quickly becomes covered with sea life and sort of disappears into the rock surroundings. Next question. If there is energy generated in excess of what local infrastructure can support, and that excess energy has to be transmitted greater distances, such as from Humboldt to San Francisco via subsea transmission cables, what is the expected energy loss? If 1 unit of energy enters the cable at the source, what percentage of that cable, of that unit will remain at the landing site of the cable? Steve or Eric, you want to tackle that?
Yeah, and it's usually a couple percent. I can't give you an exact number without having some design details. There's a fundamental principle in my line of work called Ohm's law. It's a fairly simple calculation, and if you want to have lower losses, you increase the voltage higher and put in more conductor. Increase the size of the conductor, and it's part of the equation in all of this. Obviously, you don't, because when the energy that doesn't make it to the other end of the cable is dissipated as heat, and you don't get paid for heat in the ocean water. You only get paid for what you deliver. So it's a design parameter, and you'd want to keep it just a couple, a few percent. I really can't answer it any more exactly than that.
Thanks for that. So there are a number of questions that are related to commercial fishing and interactions of gear and transit with offshore wind. And beyond the scope of today's topic, but these are extremely relevant topics that will be discussed for the foreseeable future. There are a variety of ways that this gets addressed, both in the early planning process, as well as when we actually get around to site selection and design of the facility, so as to minimize impacts on users. But we're very cognizant of this issue, and we're not neglecting this today. It's just not something we can cover from a transmission perspective. Again, questions are like, what happens if a cable gets snagged by fishing vessels? Where does the liability lie? Again, another question I'm probably not prepared today to address directly. I will point out that I see that Scott McMullen was on the call earlier, who runs the Oregon Fishermen's Cable Commission. There's a great deal of knowledge, expertise on that topic with Scott. Encourage you to reach out to Scott and learn more from his perspective. And of course, there's a lot of experience with this from the European experience with offshore wind, where there has been a decade and a half of installed wind and interactions with the fishing community. So lots of lessons that can be learned for how best to address these various issues. Here's the next question. I assume that if they link the transmission cables in the wind farm from generator to generator through the use of mid-water cables instead of on the seabed or burying them, that it would reduce costs. If I heard correctly, the developers like the mid-water option the best. Are the cost savings the primary reason the mid-water option is their preference? Steve, you want to maybe tackle that first?
Yes. As I mentioned, when I showed that slide with the three alternatives, I did mention that the one with the mid-water cables is what's most popular at the moment. And that's partly because it's lower costs and it works. It's a fantastic solution for the prototype systems where they're installed. When we come to an actual field development such as this, we have to go back to first principles, and that's the way I'm taught and I work. What are we aiming to do here? What's the safest way to do it? Safety comes first, and then we've got to look at what are the costs of the different alternatives. And it may be mid-water, it may be bring the cables down and then back up to a transformer station, or it may be to leave everything on the seabed like I showed on the last slide. It must be considered on a project by project basis. Hope that helps.
Yeah, thanks. Question here, in addition to an RTO, regional transmission organization, or a merchant developer, could another option for offshore transmission be an offshore equivalent of BPA? John, I think that's directed at you.
Yeah, you certainly could have a power marketing agency, federal power marketing agency created that would ultimately be responsible for the development of the transmission offshore. But once it gets onshore, it still has to go into something, and so that's where you need an RTO ultimately, and you need an RTO to be able to deliver and provide the market structure for the power that can work effectively.
It's an interesting point that we can design all sorts of really cool things, and the electrons don't care about human construct. However, humans do, and the features and the organization that John's referring to are absolutely essential to grid operations today.
Thank you. Additional question here. Could an offshore backbone be designed to relieve onshore grid congestion as well as to integrate renewable energy?
I'll try to address that one. Yes, I think so. Ultimately, I mean, I've seen economic studies that show that if you do a offshore backbone on the East Coast from the Carolinas to New England, you could do that backbone simply for the economic purpose of relieving congestion or economic dispatch from without any offshore wind at all, and it still would make sense. So there are great opportunities for an offshore backbone if it goes long enough, along the coast. Certainly, I think there was discussion about all the solar in the Southwest. We could utilize the backbone to deliver some of that solar in the Southwest to, areas of the Northwest where there's loads in Oregon and Washington. So there is potential for that additional economic diversity through that kind of a backbone system.
Steve or Eric, anybody else want to jump in on that?
Well, I'll just say that John, in your presentation, you alluded to the load flow studies that are done as part of planning such an installation, and it would be a key feature of that would be considered when you're going through a thing called the path rating process. So yes, it is entirely possible.
Next question. There was some mention of wind tower positioning having to be a certain distance apart in order for the towers to use wind efficiently. What was that distance?
The guidance I'm getting there, we haven't done the calculations yet. It's still very, very early days. But the guidance I'm getting from my colleagues in the UK is that we're looking anything from 5 to 9 diameters, wind turbine diameters apart. So with the wind turbine, the recommended distance at the moment for the 15 megawatt turbines is something like 240 meters. We're going from about 1.5 kilometers to 2.2 kilometers. And that all needs to be worked out on a field specific basis with the experts. And there's no way we've had time to do that work. Does that help, please?
Thanks for that. And I've heard NREL quote National Renewable Energy Laboratory quote 8 times diameter. So clearly there's a range. And I will say I did not follow this link, but I did see a heading that suggested that we're learning that the distances, the so-called shadow effect is what we were talking about here. We're trying to minimize the effects of downwind on subsequent turbines, where if you position them too closely, it degrades the wind quality and does not work as efficiently. This appears to be the case. There might be less actual shadow effect than we originally thought. So we'll watch that and it will probably continue to develop. Next question. Would there be any interactions between HVDC, high voltage direct current, offshore transmission options, and offshore substation sizing and costs? Like, would offshore substations cost be higher with or without an offshore backbone line? Any early indicators on this? Maybe no impact or difference?
If I could address that, there really are a couple different things you have to consider. You're going to have, as I described, a collector substation, and what you feed with that collector substation is largely not going to affect. There's a little bit of a cost, but not a huge one. It's where you feed that to, and that you have a convenient point of interconnection that the developer doesn't have to pay for, so that their project is frankly more economically viable. That really is where you have to go to. So I'm not sure I'm exactly answering the question you're getting at, but I am using your question to emphasize the need for that convenient point of interconnection and coming up with a way to finance that. So the whole burden isn't on the project developer. That's my thoughts on it.
Anyone else, Steve?
Yes. We're seeing in Europe a tremendous amount of work looking at how best to optimize the gathering systems, just as John has been talking about here. And they're going for large centralized substations, and with the smaller gathering stations feeding it in, much as Eric has been describing. When I see the work, the European work, which what John's talking about is along very similar lines. We've got to recognize that there are different ways of doing it, and there will be different costs with it. And it's no surprise, as I sidestep again, this all needs to be looked at. This is not a simple solution. And it's going to take a considerable amount of work to go through and to look at the alternatives and to justify things, to look at what other people are doing, to learn from them and to incorporate it. It's going to be a major study topic. Does that help?
Yes, thank you. Next question. How is Europe handling similar grid planning issues, financial, environmental, logistical? Maybe focus on cooperative government industry planning organizations in the North Sea area that have been created, such as WAB, Offshore Wind Energy Business Network for Germany.
Shall I answer that one?
Sure.
What I'm seeing in Europe, the major gathering point is within the North Sea. And we're seeing interconnection lines between Norway to the UK, Denmark to the UK. I was reading one yesterday about I think it was off Denmark. They're putting in a small man-made island, which will handle many gigawatts. And that from Denmark, it's going to be fed into Germany and into the Netherlands and into France as part of an integrated collector and gathering and distribution station. Another one I saw was a potential gathering system between the UK and France, where there was one single large gathering station, many megawatts, many gigawatts actually. So these are being worked on, and these are being actively investigated to do just as John is suggesting here.
Right, and I'll add that I have seen some sort of lessons learned type articles out of Europe where each company has to date, more or less generally true, been responsible for their own generation tie, radial line to shore, which incentivizes companies to develop projects as close as possible to shoreside infrastructure, which is in some cases entirely appropriate, but also begins to create problems of proximity to view sheds, concentrated use areas around ports, et cetera, and just concentrating the development closer to shore. The sort of admonition that I've read over the last few years is that, hey, US, as you begin your process, you should learn from Europe and our approach and maybe consider planned systems that concentrate development around shared infrastructure. So it's part of the reason why I began thinking about this very topic and how we might learn from those lessons in Europe. Next question. Any value in discussing the considerations and trade-offs of the first entrance of a Pacific Coast floating offshore wind project being sized as smaller pilot project versus larger commercial scale, whatever those relative megawatts, gigawatts might be? And I'll start that one, which is clearly, we all think that for the first projects to get developed, the project has to be balanced in terms of being too small or being too large. If it's too small, it does not serve the purpose of answering the questions that we need answered in order to move forward with permitting of larger projects. Cumulative effects in particular is a very important topic that needs to be addressed. You can't do that by putting a couple of turbines in the water. At the same time, nobody's interested in freaking everybody out by proposing, a gargantuan project that's just not justified, given that it's a new use of the ocean. So this is a very relevant question, and many of us have been chewing on this for some time. I would finish that by pointing out that note that the intent of a pilot project is not necessarily to demonstrate the viability of the technology. The technology already has been demonstrated. So that's not necessary at this point. And I'll finish by saying that, for someone to pay for a project, a company to make an investment in an offshore wind project, it's got to pencil out at some level. They can maybe start being a loss leader by getting the first project in the water, but at the end of the day, they have to pencil out. So if it's too small, that's just not going to happen because the cost of infrastructure is too great. Anyone else want to jump in on that one?
Yeah, if I can add to that, Jason, what I see here is risk and risk management. And we're looking at I explained within my presentation how all these technologies were coming together. But let's recognize nobody has put a 15 megawatt floating wind turbine in the sea and have it working off the coast that we're looking at here. At some stage, someone's got to evaluate the risks, and we might be looking at later on, how do we minimize risks? Do we go with one company? Do we go with multiple companies? And so how we manage risk is going to come up. And is the best way to manage risk with a small demonstration project like you're talking about, Jason? We need to look at that in a lot more detail. but certainly it's one of the options that we've got out there to give us greater confidence to move forward. And bearing in mind, these projects are going to be a lot of money. And if we get the wrong technology offshore, it's going to be problematic for us. So we must work our way through this and make sure we've got the correct solution. And that may involve offshore testing.
Thanks, Steve. So we've got a handful of questions in only a few minutes, so I'm going to push forward. Is it conceivable that offshore wind development in Northern California and Southern Oregon will require both new subsea and transmission development? Presumably transmission means terrestrial. Would it be advantageous from a financing perspective to bifurcate as two projects? John, maybe you have some thoughts on that?
I'm not sure I completely understand the question. You can't bifurcate it if in fact you have to do the onshore, what they call network upgrades, to ensure the reliability and stability of the offshore project. There's no bifurcation there. It's all part of one continuous requirement, and so the costs should be spread, similarly over the same population.
Okay. Pushing on here. What happens if there's a failure, a rupture, or a break in the transmission cable?
Well, in the immediate term, you have protection equipment that will detect the fault and de-energize it in a fraction of a second. That's the fast part. The long part is you have to fix the cable, and that's a challenge. And there's a couple of technologies that are used for it, but to be frankly, that's kind of a nightmare scenario, and it's why cables are so thoroughly tested and there's so much rigor put into their manufacture and design to, which makes such faults, relatively uncommon. Now, eventually cable may wear out, and if it's at its end of its useful life, in some fashion would have to be replaced.
Okay, so there's maybe two that can help finish this out here. First of all, Steve, why would the long distance transport cable need to be in shallow, less than 100 meters of water?
It doesn't. What we've got is we have to get the end terminations in the dry. We have to make sure that the cable itself is not in dynamic mode. So it's secured in a way that it doesn't flop around all over the place. And when we talked about doing this over the last few weeks, we were saying, well, why not put a fixed platform in about 100 meters? Because we know that's doable. But really, these fixed platforms can go out a lot further should the need arise. And like I mentioned before, we've got to find the right location for this. We've got to look at the water depth. We've got to look at materials. And once we've identified the optimum solution for the main transformer station, then we can look at how and where we run the power cables. Because these power cables will certainly go down to hundreds of meters, if not 1,000 meters. So I'm not worried about the depth of the power cables. It's just making sure that we can make the end terminations in the dry, and that needs to be a suitable platform for it.
All right. Well, that brings us to the end of our time here today. We did manage to get through all but 2 or 3 questions, so apologies if yours didn't get answered. But I want to take this opportunity to first of all thank you all for participating today. I hope you found this informative. And I would like to reiterate my request that you reach out to me and raise issues of concern and interest regarding this potential solution opportunity. And I want to, of course, thank our presenters today who have put a lot of time and effort into bringing this material together for you today. So thank you all so much for your efforts on this. And I want to again thank Eric Hell and his colleagues at Power Engineers for supporting today's webinar. It allows POET to continue to bring these kind of events to you and help us achieve our goal of addressing climate change through the promotion of responsible development of marine renewable energy. So with that, thank you all very much. Have a great rest of your day.
Thank you. Goodbye.